All right, welcome to tonight's lesson. So in this lesson, we are going to be looking at statics, and to be specific, we're going to be discussing the dot product of vectors. So the same dot products that you learned in mathematics, we're going to apply them in solving mechanical equations. All right, so rather mechanical questions. All right, so if you have any questions, or you want to reach me for any reason, or you want to join the lessons, or there's someone who wants to join the lessons, they can just contact me using these lines on the screen. Right, so the objectives, we've covered almost everything. I think we're on the last part, the last point here, to introduce the dot product in order to determine the angle between the vectors or the projection of one vector onto another. So this is the last point. Then from there, we're going to look at other stuff in statics. All right, so let's quickly begin. All right, so what is the dot product? What do you understand about the dot product? So the same things that you learned in your first year, mathematics, and in physics, I think you did this, though it wasn't detailed, are the things that we're going to start learning even here on the dot product. So we all know to say the dot product is simply just an equation which is well known as A dot B being equal to the magnitude of A times the magnitude of B times the cos of theta. So this is the dot product. So the magnitude, when you find the magnitude of A and the magnitude of B, and then you multiply it with the cosine of the angle theta, and then this theta is just the angle between 0 and 180 degrees, meaning we're talking about the first and the second quadrant. So this is what you have as the dot product. This is what we know as the dot product. So this is what we're going to apply to solve questions. So it's as simple as you are seeing it right now. And one thing that you have to understand again about this part is that when you have two vectors, vector A and vector B, you have, let's say for instance, you have AI plus BJ. You can also have CK. And then you also have XI, YJ, and ZK. Then you've been taught to find the dot product of these two vectors. If you don't want to use, if you don't have scalar quantities, or if you don't want to use their magnitudes to find the dot product, what you can just simply do, or let me say, if you have not been given the angle between these two vectors, and then you've been asked to find the dot product, what you just have to do is to multiply the corresponding terms. So for instance, in this case, we're going to multiply A and I there. Or let me make it clear to you. Let me just say the dot product, if you have this as your dot product, what you just have to do, if they ask you to find A dot B, if B is X, I, Y, J, and Z, K, then they ask you to find A dot B. So A dot B is simply just going to be equal to it's just the normal multiplication of vectors. You multiply this and that one. So you're going to have AI plus BJ plus CK being multiplied by XI plus YJ plus ZK. So you multiply everything the normal way we multiply mathematical equations. But as you are multiplying, you have to put in mind that I dot I is going to be what? 1. So wherever you're going to have I dot I, J dot J, this is also 1. Where you're going to have K dot K, this is also 1. But whenever you have I dot J, this one you always have to replace it with 0. I dot K is 0. I J dot K is 0. All the other different different what's this groupings when you group them together into two groups, yeah, into two pairs rather. So when you group them, whenever you have two different unit vectors multiplying themselves, you put a 0 there. When you have the same vectors, unit vectors multiplying themselves, you put ones there. And you are going to come up with a solution that is going to be, oh, that is going to look like this one. So it's going to look like this one. So your A dot B is going to be equal to, so you find that A is multiplying with X, and then you have B being multiplied by Y, and then you have C being multiplied by Z. So what that means is that if you want to find the dot product given two vectors, you simply just have to multiply the corresponding terms. You multiply A and X, and then you say plus B times Y, and then you say plus C times Z. So this is just a quick revision about the cross product, rather the dot product. And then if you've been given the dot product of two vectors, or if you've been given two vectors like this, and then they ask you to find the angle. So what you just need to do is to make cos theta the subject of the formula. You're going to have cos theta being equal to A dot B, and then everything divided by the magnitude of A times the magnitude of B. And the next thing is that the next thing that you need to consider, or that you have to put in mind, is that after finding the dot product of two vectors, you have to find their independent magnitudes. So you're going to find the magnitude of A. So the magnitude of A is therefore going to be equal to what? Our A is here, so the magnitude is going to be A squared plus B squared plus C squared. Then the magnitude of B is also going to be found by saying X squared plus Y squared plus Z squared. So this is how you find their magnitudes, and then you divide them into the dot product which you have found there. And then to find the angle, you simply just have to say the cos inverse of what you are going to have. So let me just write it properly. So the angle will therefore be equal to the cos inverse of A dot B over the magnitude of A and the magnitude of B. So this is what you're going to have as the angle between these two vectors A and B. So what I've just written here is a summary of everything that we're going to learn. All right, so let's quickly move on to what I have prepared. So we have these few notes here. Occasionally, in statics, one has to find the angle between two lines or the component of a force parallel and perpendicular to a line in two dimensions. These problems can readily be solved by trigonometry since the geometry is easy to visualize. In three dimensions, however, this is often difficult, and consequently, vector methods should be employed for the solution. Yeah, so the dot product, which defines the particular method for multiplying two vectors, will be used to solve the above mentioned equations. Mentioned problems. All right. So the dot product of A and B can be written as A dot B and be read as A dot B. So this is what I've sorry for that. All right, so this is what I've explained. I got choked. Okay, so I've explained all this. I've already made a summary of this. So if you have the vector A and you also have the vector B, you can find the dot product of these two vectors. And the angle between them is supposed to be from 0 to 180. And then A dot B is given by the multiplication of the magnitude of A and the magnitude of B cos theta. Okay, so the dot product also obeys all the three laws of operation. So we have the commutative law, yeah, the commutative law, which is A dot B there. Yeah, so commutative law, I'm sure you all understand this because commutative just talks about the arrangement of the terms. So if you have the vector A and the vector B there, when you find A dot B will simply just be equal to B dot A. So when we start discussing the cross product, this is not true. So for the cross product, A cross B is not equal to B cross A. They are not the same. So the cross product, this does not apply. But for the dot product, A dot B is the same as B dot A. And then when you multiply the scalar to a dot product, is okay. What I can just say is that this is just normal multiplication. So when you multiply the scalar to the dot product of two vectors, you can simply just multiply that scalar with either vector A or vector B. What that means is that if you have A dot B and you also have the same A dot B, so, and you multiply A to the dot product. So this can also be written as A times the vector A dot B. The answer that you're going to get here is simply just going to be the same as the answer that you're going to get when you first just get A and multiply it with a scalar times the vector B. So this is what it means. All right, so the distributive law. So when you are finding A dot, the addition of two vectors B and D, this is just the same as, or rather this can be distributed and found to be. So you can have A multiplying with vector B there. So you're going to have A dot B, and then you get what is in between, the sign that is in between there, write it there. And then you also distribute A and D there. So you have A dot D. A dot D. So it also obeys the distributive law. All right, so let's quickly look at what follows. So how do we formulate this in Cartesian form? So I've explained this, though I didn't follow the whole procedure. But one thing you just have to understand here is that I times I is 1, I times j is 0, ik 0, jk 0, 1, 0, 0, 0, 1. So we're just going to remain with this term, the ones that are giving us ones, this term, and that term. And then the rest of the terms are going to give us zeros. So the rest of the terms are going to give us zeros. And these are the ones that are going to have as ones. This one is going to give us 1 times this. You're going to get 1 times that. You're going to get 1 times that. Then the rest of the terms are going to give us zeros. All right, so we quickly move on. So this is the result you're going to get. And the dot product of two vectors always gives a scalar, or it gives a constant. In short, it gives us, it gives a constant as the answer. So when you combine, rather when you find the dot product of two vectors, you're going to get the, what's this? Okay, so when you multiply, or when you find the dot product of two vectors, the answer that you're going to get is going to be a scalar quantity, or it's going to be a, okay, not really a scalar, let me say, it's going to be a constant, yeah. Let me just put it as a constant. Okay, so when you multiply two vectors A and B, or you multiply three vectors A, B, and C, you still get Oh, right. Sorry. When you multiply two vectors, A and B, you're going to get a constant as the solution. Let me end there. Let me not add other things. Okay, so this is the solution that you get. This is the, I think I explained this when we just started on the first page there. All right, so how do we apply the dot product in statics, or what do we use, or how do we use the dot product in statics? It's simple. So the dot product has two main important applications in mechanics. Yes, you have a question?
Yes. Hello.
I'm getting you.
On the previous slide.
Okay. Okay.
So when we are using cross product, let's say for example I times j, will it give us 0 or some other number?
When you're using
Cross product.
when I'm using the cross product, so the cross product of two different, what's your question, by the way? You're saying when you're using the cross product and then you're finding what? Two vectors, the cross product of two vectors.
Yes.
A cross B is simply just the magnitude of A times the magnitude of B, and then this side you just put sine theta.
Okay. All right. Okay.
What was your question? This was your question. For dot product, there is cos theta this side. Then for cross product, there is sine theta. Then for cross product, I think I got your question, but I just wanted to be clear of what you were trying to ask. Okay, so for cross product, okay, let me just add it on in case maybe that's not what you wanted to ask. For cross product, when we find I, though we're going to learn this, when you are finding I, okay, it's like this, huh? Let me show you this in advance, though we're going to have time when we're going to learn this. So we know that we have I, then we have J, then we have K. So when you are going clockwise this side, you are going to be having positive values. So when we say I cross J, the answer will be K. J cross K, J cross K, the answer will be what? I. K cross I, K cross I, the answer will be, oh, sorry, this is I. K cross J, the answer will be K cross I, sorry, not T. K cross I, the answer will be J. So when we begin to go back, when you're going the other way, when we say I cross K, I cross K, the answer is negative J. And then K cross J, K cross J, the answer is negative I. So you can know this just from this, from what I've drawn there. And then J, oh, sorry, J, I always have problems in writing J and I. So J cross I, the answer is, so J cross I was still going back, so this would be a negative K. Yeah, so and that is it. That is what you're supposed to do. So if this is the question that you're asking, this is what normally happens. Yeah. So I don't know if you have any questions or we proceed now.
That's all.
Okay. So the dot product has two important applications. The first application is the one that we talked about, which is calculating the angle between two given vectors. Yeah, so it helps to calculate the angle between two given vectors. That is the dot product. And then the other thing is that it will help us to find the projection of one vector onto another. What it means is that, okay, let me just display something. So for the angle, it's straightforward. I explained this when we just began. And then for the projection, it helps us to find the projection of one vector onto another. So what that means is that you can have, let's say, a vector A. You can have a vector A, then you want this vector to be projected along this axis. So what you do is the projection, or how you find the projection is simply just, or let me say the projection of this vector along this axis is going to be given by vector A subscript A. And this is going to be the magnitude of A cos theta. So this is how we find the projection. Okay, so I'm sure we're going to understand this when we do some when we do the exercises that we have. All right, so in other words, if you're using the unit vector, if you find the unit vector, or if you have, or maybe if this projection, or in this line where you want to project your vector A, this line is defined by a unit vector UA. To find the projection of this vector A along the unit vector UA, you simply just have to multiply that unit vector with the scalar quantity of A. So to find the vector quantity of, find the vector or the Cartesian components of the vector A along this projection, along this projection, simply just along this, the unit vector directed along this line, or directed along UA. Or let me say the unit along the unit vector UA. You simply just have to multiply your unit vector times the scalar of, or rather the value of that force that you've been given. But I'm sure you understand this better when maybe I do one question. Okay, so we have this question here, which says, determine the magnitude of the projection of the force F onto U and V axis. So this one is straightforward. Like I said, if there is a 90 degrees somewhere like this, you don't have to, okay, let me change the color. So if you have a 90 degrees like this at some point, this one is straightforward, because we are just going to use the normal SOHCAHTOA that we know. Yeah, actually, when you're dealing with projections, SOHCAHTOA also applies when there is a 90 degrees. Yeah, so to find the projection of this force F directed along, or the projection of F onto U and V. So let me start with V. Onto V is going to be this same force, which is 100, and then it's being projected onto V. So we're just going to say cos, because this is adjacent, this projection, or this line where I want to project this force is the adjacent to to this angle 15. So we say cos 15 degrees. So the answer that you get there is the solution. So this is going to be 100 cos 15, and this will be 96 point, this is going to be 96.6 and 6.6 newtons. And then for the projection along the u-axis is going to be 100. It's going to be 100 cos. It's going to be 100 cos 45 degrees. And this is going to be 100 cos 45. This is going to be 70.1. So this is going to be 70.1. 70.71, sorry. 70.71 newtons. So these are the projections. They're just as simple as that. Maybe it's just the way I was explaining them. Maybe that's why they seemed to be a bit confusing. But anyway, we understand. Let's look at the other example. Okay, so these are the answers. All right, so let's look at this example here. This one is quite involving. So you should follow me step by step as I solve. So the question says, the frame shown in the figure, is subjected to the horizontal force F. So we've been told to say the force is horizontal, meaning it's in the J or it's in the Y, because what we have here is in 3D. Determine the magnitude of the components of this force parallel and perpendicular to the member AB. So every time we're trying to calculate, anything or a force along a given or along a particular line, we always have to use what is known as a unit vector. You always have to use a unit vector along that same line. Then you multiply it with the force to get the vector along that line. Okay, so let's find the unit vector along or directed along AB. So how do we find the unit vector? So we first find the coordinates of A, B, or we can simply just find the coordinate of what? Of B. If we get A as the initial, or the origin, so if taking the coordinates of AB or along AB is just the same as getting the coordinates of B there, because when we say B minus A, if A is 0, if A is taken as the origin O, B minus 0, the answer will still be B. So it's just the same as taking the coordinates as B, at B alone. So we say the vector along AB, so I'm going to call this AB, is going to be equal to, so the vector along AB is going to be equal to, so we just get the coordinates of B. So the x coordinate of B, we know that it's from that point to that point. So when you look at that distance there is what? It's 2. So it's directed along the positive x, so it's going to be positive 2i. And then in the y, it's from that point to what? To that point. So this distance there, if you check, it's 6. So we have, and it's also directed in the positive y, so this would be 6j. And then we also have the z, which is from there to that point. So when you check the distance from there to there, it's simply just 3. So it's going to be positive 3 k. So this is what we have as our vector. So let us find the unit vector along this, in this same, let us find the unit vector, or let us find the, let me just say the unit vector of AB. So how do we find that? So we first have to find the magnitude of AB. So the magnitude of AB is going to be equal to the square root of 2 squared plus 6 squared plus 3 squared. And this will give us what? So this will be 4 plus 36 plus 9, and this is going to give us 39. So rather 49. So the square root of 49 is 7. So to find the unit vector of AB, so the unit vector of AB is therefore going to be given by the vector AB. So this is the vector AB. So the vector AB divided by the magnitude of AB. So this is just going to be 2i over 7 plus 6 over 7j plus 3 over 7k. So this is what you're going to have. And then having found this, we are now just supposed to multiply this by 300. I mean, not really 300, but by this force for you to get the scalar, rather for you to get the what is the force, or rather the projection or the component of this force F along or parallel to this line AB, or to the member AB. So how do you do that? So in other words, we're just trying to find the dot product of F and this vector. So finding the dot product of F and the vector AB and the unit vector AB, this is going to be equal to, we're going to have 2 over 7i plus 6 over 7j plus 3 over 7k. We're multiplying this with what? With 300j. But when you look at this one is only having j, and we don't have I and k. So multiplying this j times k will give us a 0. J times j will give us 1. So there we're going to have 6 times 300. We're going to have 6 times 300, then divide by 7, which gives us 257.1. So we're getting 257.1. Then multiply this j times I there, you get a 0 as well. So this is the vector, a scalar quantity. I mean, this is the value or the magnitude of this vector projected or directed along the component or the member AB. So this is the solution for the first part. Then how do you find the perpendicular? So the perpendicular, the way you find the perpendicular is you simply first have to multiply this same quantity that you have found, which is 257.1. You are going to multiply it with the unit vector again, so that you get the vector quantity of this same force, which is along the component or the member AB. So you multiply this 257 with the unit vector. So when you do that, so when you multiply that with that, you get the solution. So the solutions that you are going to get there are the ones now that you have to subtract from this one, because at this point, you're going to have something like this. Let me just draw something here, which will make you at least understand. So at B there, you're going to have something like this. And then we're trying to find the unit vector of this one. We have found it. The unit vector of this line, and it's the one that we have found there. And this is, if you multiply or if you find the dot product of this same line with this force here, it means that you have found the value of this force along this same line here. And then after finding the unit vector, if you want to find the perpendicular, the value of the perpendicular component of this same force here, what you just need to do is that you take this as your resultant. So if you take this as your resultant, it will be like this. Then you're going to have something like this. So if you take this as your 90 degrees and you are trying to get the what is the value of this vector there, means that you're going to say the vector f is going to be given by negative AB. So this will be negative AB, then plus what? So this will be negative AB, negative AB, what, moving from there to there. So this will be negative AB. Okay, we're trying to find this one here. I forgot, sorry. We're trying to find this force there, which is the, okay, I'm going to call it the perpendicular force to AB. So we're going to have this perpendicular, oh, sorry, that's not a symbol for perpendicular. So perpendicular is going to be like this. So we're going to have something like this. Then this is going to be, so for the perpendicular force means that we're going to move from there and then we'll go like that. So moving from there to there, we're going to move negative AB. And then the reason why I'm adding a negative is because we're moving against the direction of AB. AB is from there to there. Now we're moving against the direction. So we're going to say negative AB, and then we say plus the force itself, which is F, so plus F. So this is how you find the perpendicular component, and then you find the magnitude of the perpendicular component by just finding the vector that we're going to find here. You find the square root of that vector, the square root of the vector there, then you square all its terms there. Okay, so I don't know, but I'm sure maybe you've gotten the concept. Let me just display the solution. So this is what we found. Okay, so this is the solution that we found. And then to find the expression of this in the Cartesian, remember what I told you, simply just have to multiply the same 257, which we found, which was the force, you multiply it again with the same unit vector there. And then you get the solution in terms of a vector. Yeah, so this means that it's no longer a scalar there. It's no longer a scalar S, but it's now in a vector form. It's now in Cartesian form, rather. Okay, so from there, the other thing that you now need to do is to find the perpendicular component of this same force directed along AB. So if the, so if this ends, I think you should join using the same link. Yeah, so how do you find the perpendicular component? You simply just have to subtract. I think I showed you from this. I drew something like this, and then I showed you how I came up with that. And then you simply just have to subtract the force there, which is a 300 newtons, and then minus the vector, the Cartesian component that you found there, the Cartesian vector that you found there, subtract it from the main vector, which is 300. Then whatever that you get there is the one that you use to find the value of the perpendicular vector. All right, so there's an exercise at the end which you are supposed to do. I think this is the end of tonight's lesson. See you in the next tutorial.